In this video, we're going to discuss the topic of chemical equilibrium. The objectives of this video are to gain an understanding of what a chemical equilibrium is, an equilibrium reaction, as well as to be able to use K sub C, which is known as the equilibrium constant, and the mathematics connected to it, known as the equilibrium expression. Before you can begin working on these concepts, however, you need to have a good understanding of how to write and balance a chemical reaction, conversions into and out of the unit of moles, as well as the idea of concentration, particularly concentration as measured in molarity. We can begin our discussion on chemical equilibrium with a quick review of your standard chemical reaction. While they're all different, they tend to follow the general format of some chemical A reacting with another chemical B, and these two combine to form new substances which we'll call chemicals C and chemicals D. The letters in capital represent our new chemical substances, whereas the lowercase letters here are the results of the balancing of this chemical reaction. We have a certain number of this chemical reacting with a certain number of chemical B, and as a result we get a certain number of chemical C and a certain number of chemical D. An excellent example of this would be the very straightforward reaction of the chemical propane reacting with oxygen gas, the combustion of propane. When these two things combine, the end result is carbon dioxide being formed, CO2, plus a little bit of water. When we go to balance this chemical reaction here, we put a 2 in here and a 2 here, meaning for every 1 mole of CH4 that reacts, it reacts with 2 moles of oxygen, creates 1 mole of carbon dioxide, and 2 moles of H2O. Again, this is something we've seen over and over again throughout the year. Here we can see that reaction in play. The bubbles are filled with CH4. As they come in contact with the candle flame, we can see them catch on fire. We know enough chemistry now to know also that the carbon dioxide in the water is created, as we predicted before, in the stoichiometric amounts that we talked about. So again, so far, nothing new. We have a regular old chemical reaction. Our methane reacting with oxygen gas to create carbon dioxide and a little bit of water. Now to get into this whole concept of equilibrium. In these reactions, the reaction we've talked about so far this year, our reactants are what react together to form our products. But the new question is, what would happen if our two products could also react together and likewise go back and create the CH4 and the O2? We get a new reaction that would look like this. CO2 plus 2H2O would react to yield CH4 plus 2O2. Now we certainly don't expect this to happen with this particular reaction, but there certainly are reactions out there that do that. For example, we can take this reaction. NO2, which is nitrogen dioxide, can react to yield N2O4. And again, we can do a little balancing here. But just like this forward reaction can go, we can also have the reverse reaction go as well. And we show this by drawing the 2 arrows, meaning this reaction happens in the forward place. When two NO2 molecules come together, we would expect them to combine and create the N2O4. But likewise, once the N2O4 is created, it can break apart and go back and form the two NO2 molecules. And you can imagine that these two reactions compete with one another. We have this forward reaction, which is this guy right here, going all the time, and likewise we have the reverse reaction happening all the time. This is what we refer to as an equilibrium. There's a balance between how much forward reaction is going, creating the N2O4, and how much reverse reaction is going to create the two NO2 molecules. Here we can see a very striking example of an equilibrium. This is what's known as an iodine clock reaction. And as you can see, we can see the color of this substance going back and forth between these two different colors. You get the forward reaction going, creating a certain compound that's yellow, and that reaction then goes backwards again, creating another compound which is blue, and this happens over and over and over again. So now we have a new way of thinking about chemical reactions. They not only go forwards, but they also go backwards as well. Let's think of our nitrogen dioxide reaction again. 2NO2 reacts to yield N2O4, and likewise that N2O4 goes back to yield the two NO2 molecules. We draw these double arrows now as a way of showing there's a forward reaction and a reverse reaction. As we said before, the amount as the NO2 molecules react with one another, they combine to make N2O4, and simultaneously the N2O4 molecules that you've just created react again to go back to create the two nitrogen dioxide molecules. And again, we call this an equilibrium. There's a balance between how fast the forward reaction goes and how fast the actual reverse reaction goes. We can actually even keep track of that balance mathematically with what is known as the equilibrium constant. The equilibrium constant is a mathematical expression that keeps track of how fast the forward reaction is going versus how fast the reverse reactions are going. And the way it works is we keep track of concentrations, and we use brackets to denote concentrations. We're interested in the concentration of the product divided by the concentration of all the reactants. So based on how large the value of K sub C is, we can get an idea of how this balance actually sits. Does this balance create more product, or does the balance create more reactant? For example, if K sub C is equal to a very large number, that means we have created in our balance more product than reactants. If you look at the mathematics up here, we can clearly see that. If K sub C is a large number, that the value on top here, the product number, must be significantly larger than the concentration of the reactants, which means we're getting significantly more forward reaction creating the N2O4. Likewise, if K sub C is a very small number, we would expect our reactions balance to favor more of the reactant side than the products. We can clearly see again, if the value of K sub C is tiny, that must mean our reactants term is very large, whereas our products term is very small, thus resulting in a smaller result in the value for K sub C. And again, we would see more of this reverse reaction occurring than the forward reaction, and we get a lot more of our NO2 formed than our own N2O4. This value of K sub C is constant for any chemical reaction as long as all other conditions are kept constant as well. Temperature, pressure, and a lot of other variables can affect this balance, and that's something we can discuss later, known as Le Chatelier's principle. To wrap things up, we have two quick examples that we can take a look at. First, we'll take a look at this reaction. COCl2 reacts to yield carbon monoxide plus chlorine gas, a very simple chemical reaction. And just like the ones we've been talking about, not only the forward reaction goes, the decomposition of COCl2, but the reverse reaction goes, which is the synthesis of the COCl2 from the carbon monoxide and the chlorine. We can write a K sub C expression for this reaction, in which case we'll put the products over the reactants. Well, our products here would be the concentration of carbon monoxide times the concentration of the chlorine gas divided by our reactants, which are just the concentration of the COCl2. Now you could measure at equilibrium, once you allow the reaction to establish that, we can measure the concentration of the carbon monoxide, the concentration of the Cl2, and the concentration of the COCl2, and we would get a number, and we would find out that this K sub C value, if we plugged all that information in, comes out to be 2.2 times 10 to the negative 10th. You'll notice, by the way, that this number is unitless. Concentrations divided by concentrations all cancel out. Now the question I have for you as you're watching this is, does this reaction favor creating more products, i.e. is the forward reaction happen, this guy here, or does this reaction create more reactants? Does the reverse reaction happen more quickly? And you should be able to figure that out based on the magnitude of this number. Pause the video right now, take a moment to think about it, and see if you can come up with an answer. Hopefully you had a chance to check that out. This value here is an extremely small number. To the negative 10th means we're going to move our decimal place this way 10 times to get something 0.0002, lots and lots of zeros in there. And because it's a really small number, that must mean the formation of the COCl2 is favored. You divide anything by a large number, this concentration here being very large, is going to make our value for K sub C be very, very small. Likewise, the concentrations of these two chemicals must be very, very small, so that a small number here divided by a large number here ends up getting this very, very tiny value for K sub C. Let's take a look at one other example that's a little bit more complicated, and it'll take some more of this stuff into consideration. So this last reaction we're going to look at is this one. We're going to have hydrogen gas reacting with chlorine gas, and those are going to react to create the chemical HCl, which is hydrochloric acid. Again, the forward reaction occurs. These two chemicals, H2 and Cl2, combine. They form our HCl. But likewise, our HCl naturally decomposes again to go back and form the hydrogen gas and the chlorine gas. And once you get this reaction going, there's going to be a balance. The forward reaction is going to occur at a certain rate. The backwards reaction is going to occur at a certain rate. And we can keep track of that balance or that equilibrium by knowing the K sub Z value. In this case, our K sub C is going to be equal to, again, the concentration of the products divided by the concentration of the reactants. Well, our product, our only product in this case, is the HCl. It's got a 2 as its coefficient, so we would expect that to be squared. Remember, the coefficient in the balanced chemical reaction becomes the power of our concentration, divided by the concentration of the hydrogen gas times the concentration of the chlorine gas. Since both of these have coefficients of 1 before them, the powers are 1 and we leave them as is. So again, here we have our equilibrium expression. One of the things you're expected to be able to do is write the expression itself. And then I can also tell you what the actual equilibrium constant is. When you plug in the concentrations for reactants and products, you can solve this and you'll end up finding that the equilibrium constant in this case is 4 times 10 to the positive 31st. Again, take a moment, pause the video, and answer the question, what's favored in this chemical reaction? Are we creating more product? Is the forward reaction happening more? Or are we creating more reactants? Is the reverse reaction happening more? Again, the magnitude of our K sub C and the actual equilibrium expression itself over here should allow you to make that kind of a prediction. So take a moment, think about this, and then we'll talk about an answer. So unlike the previous example where K sub C was a very, very tiny value, this K sub C is a very, very large value. We're to the positive 31st power. That must mean that the numerator in our reaction, or our expression here, must be an extremely large number, and our denominator values must be very, very small. That means HCl, which is our product, must be the favored thing, and we would expect this reaction to happen in the forward direction. And since this number is so very large, we would expect this reaction to happen almost exclusively in the forward direction. We would expect very, very little of our H2 and our Cl2 to be created, whereas a lot of this HCl would be created as a result of the very, very large equilibrium value here. To summarize this video, a reaction is at equilibrium when there's both a forward and a reverse reaction. The forward reaction is what we're more used to throughout the year, which is when the reactants combine to form products. What's new today is the idea that the reverse reaction can also occur, where the products combine to form reactants. As the forward reaction and the reverse reaction occur simultaneously, you get chemicals cycling back and forth between products and product and reactants, and this generates a balance. And that balance we refer to as equilibrium. We can measure this balance with something known as the equilibrium constant, or K sub C. If K sub C values are very large, that means we have a lot of products formed. We say that the products of the reaction are favored. If K sub C is a very small value, we say that the reactants of the reaction are favored. We can express this mathematically in the equations we see here at the bottom of the page with our generic reaction, chemicals A and B combine to create chemicals C and D, and then chemicals C and D react back again to create A and B, the equilibrium reaction. We can see our K sub C expression is equal to the concentration of all the products divided by the concentration of all the reactants. We can take this one step further to say the concentration of each individual product, C and D, divided by the concentration of each individual reactant, A and B, all taken to their respective powers based on the balanced chemical reaction. We can plug in concentration values in the forms of molarity into all of those places, and we can use that to calculate what our K sub C value is, and then again use that to predict whether our products or reactants are favored as above.